speaker, whose slides should magically appear here soon, is Anna Scaife from the University of Manchester, where she's based in the physics department, and also Jodrell Bank Centre for Astrophysics. She's a professor of radio astronomy. She works on lots of interesting projects, including the Square Kilometre Array Radio Telescope project. And in her research, she uses lots of AI and statistical tools for highly data-intensive applications in astrophysics and astronomy, I think. Take it away.
Thanks, Catherine. Yes, so this is going to be a very application-focused talk again. Specifically, I'm going to talk about Bayesian deep learning in radio astronomy, and I'm going to focus on galaxy classification as a canonical problem that we address. So I'm going to talk about why we want to do this, and then I'm going to talk about how we are looking at recovering point-wise uncertainties on our predictions using Bayesian deep learning models, and then how those uncertainties are useful for more than just, understanding the confidence that your model is providing a prediction with. And specifically, I'm going to focus on how we use them to identify biases, and how we use them to help us preserve discovery, because that's very important for astrophysics. And I should say that all of this is something that's very fundamentally important for astrophysical analyses. I think it's probably true to say that astrophysics is the only branch of physics that's entirely based on inference. So understanding the statistics of our populations is absolutely intrinsic to the work that we do. So modern astrophysics has been revolutionized by digitization. Modern radio telescopes and telescopes in other wavebands are producing petabytes of data at this point. We're rapidly reaching an exabyte regime in terms of the data volume that we have to deal with from these observatories. And the reason for that is simply the volume of information that's available in the universe and the amount of data you need to be able to take in order to extract that information. So specifically, we work mainly towards the Square Kilometre Array Observatory, which is the SKAO, which is, in a few years, going to be taking about 600 petabytes of data per year, and has an expected lifespan of 50 years. So you can quickly imagine how much data that becomes. And within those data, there are, of course, hundreds of millions to billions of individual astrophysical systems that then need to be categorized and analyzed. So it should be no surprise that the astrophysical community is very interested in how we can automate a lot of the processing that we've been doing traditionally by scientists ourselves, because we're simply not in a regime where we can do that anymore. And that's reflected in the number of publications that you can see on the archive within the astronomy archive that include keywords such as machine learning, deep learning, or artificial intelligence, which is that nice exponential plot that I'm showing you just here. So what do our data look like? Well, astrophysics is an inherently multimodal science. We take all kinds of different data. We take images, we take spectra, we take polarization data, we take velocity data, we take time domain data. I'm going to focus on images because I think they're the most conceptually accessible. So this is a radio image of the sky, similar to the EHT images that were shown in the previous talk. However, in this image, we don't just have one black hole, but in that large orange circle, pretty much every bright point that you can see in that image is a supermassive black hole. And if you zoom in on them, you'll see that they're not just points, they have morphological differences. And so there's a few examples that have just been highlighted here. This is data from the LOFAR telescope, which is a European telescope. And I'd like you to focus on the two images on the right-hand side. So these are both supermassive black holes. We call them radio galaxies. But if you asked a radio astronomer what they were, the radio astronomer would tell you that the one at the top is a Fanneroff-Rayleigh class 2 radio galaxy, and the one at the bottom is a Fanneroff-Rayleigh class 1 radio galaxy, just from looking at the images. And that's because they are morphologically different. So to give you a couple of other examples here, you can see that the FR class 1 has its brightest regions in that jet, which is emanating from the black hole, close to the black hole, and then it has like a Rayleigh-Taylor instability type jet diffusion, and the Fanneroff-Riley class 2 is more highly collimated. It has a relativistic boosting going on. It has shocks at the end of the jets. And these are nice examples where you can clearly see the differences. An average radio galaxy will be more difficult to classify, even for a radio astronomer. But we classify them in order to understand the evolution of supermassive black holes and their environment, and by extension, structure formation in the universe. And we do that by performing population studies. So, for example, this is a sample of radio galaxies from that LOFAR data, where we're examining the two different classes of objects in terms of their luminosity, their brightness, and their size, their physical extent on the sky. These are just two of many parameters that we can associate with these types of galaxies. And from these distributions, we can hope to understand where these differences in morphology arise from. Are they intrinsic to the object? Are they a function of the black hole itself? Are they environmental? Do they depend on where the object is in the universe? Is it due to the composition of those jets that are being ejected from the supermassive black hole, or is it due to entrainment from the local environment? So these are questions that we've been asking in astrophysics for a long time. We're still asking, because every time we get new data from a new survey, from a new telescope, we learn new information that influences everything we thought we knew up until this point. So going forwards to the SKA, where we're expecting to find billions of these objects, we need to be able to automatically separate them into their different classifications and subclassifications and other types of radio galaxy that I will not go into here. However, if we want to do this with machine learning, this is not a straightforward problem. We face a number of specific challenges. Firstly, although we have very large volumes of data, we have comparatively small labeled data sets. Labeling scientific data is inherently costly because you need experts to do it. Also, we don't have balanced data sets. We have class imbalances that are due to the underlying astrophysics and structure formation in the universe. And half the time, that's actually what we're trying to work out. We need to have carefully calibrated uncertainties on the predictions from any of our models, because if we are propagating these predictions into our statistical analyses, we need to be able to understand the confidence with which they are being made. And we need to understand the biases that those models introduce into our data selection. We call these selection effects. In high energy physics, they're called acceptance functions. We spend a lot of time modeling these selection effects due to the instrumentation that we use to record the data in the first place. But when it comes to AI, we also need to understand what those selection effects are from the models. And then finally, a big one is that there are things out there that we don't know about yet. So as much as we automate our processing, we need to be able to preserve the potential for discovery. And in fact, it's the case that every major astrophysical observatory that's been built has become famous not for the thing that it was built to do, but for the thing that it discovered, because it opens up new parameter space. So I'm going to focus on these 2 points and explain what we're doing. I don't have answers to it yet, but I'll tell you what we're looking at. And then I'll come back to that discovery at the end. So when it comes to recovering calibrated uncertainties from deep learning models, I think this is a very far from solved problem. So if you ask most people how they're doing Bayesian deep learning, I would say about 90% of them, if you probe them on what they're actually doing, what they're doing is they're leaving dropout on at test time. So they're using the MC dropout approach. And so what I'm showing you here is if we take some radio galaxies as the test radio galaxies and pass them through a trained convolutional neural network that uses MC dropout, and we do 200 passes of one particular galaxy to ask the model, what class is this galaxy? Is it Fanneroff-Riley class 1 or class 2? This is what the distribution of softmax outputs will look like. So it's a simple binary classification problem, and you can see that there's a little bit of variance. There are 200 points there. So you can see that there's a little bit of variance, and that's giving you the uncertainty, if you like, I'm going to say it in inverted commas, of this model. And for 90% of the people who are doing this, that is what they get. They get the variance of their output with dropout turned on at test time. But is it right? And if I do this with another galaxy and I get a slightly different variance, is the relative width of that variance calibrated in any way? And that's the question we need to answer. So you could compare a different approach to extracting this uncertainty. So for example, you could use variational inference. So you could use another very popular technique in deep learning, which is often referred to as Bayes by backprop, and look at the distribution of outputs from 200 test passes of the same sample there. And this is for the same galaxy using the same model, trained in two different ways, and you can see that the variation in the outputs is significantly different, right? Now, in fact, it's not the absolute variance here that is important, it's the relative variance of different samples that becomes important for us. But this in itself should raise a question in your mind, which of these two techniques is giving you the true posterior over your model outputs? Well, these are both approximations to a Bayesian model. We can't get the true Bayesian posterior. It's intractable in this case. What we can do is we can get an asymptotically exact posterior. So if we use Hamiltonian Monte Carlo for this same sample, this is what the posterior distribution looks like. And once again, it is different. They're all different. Now, this is the first question we have in our mind is that, which one is correct? Well, we can say that the Hamiltonian Monte Carlo is probably the most correct. But Hamiltonian Monte Carlo is expensive, as the previous speaker illustrated very well. Monte Carlo techniques are very expensive. This is a very small model. It only has a few 100,000 parameters, but even so, it takes about 200 hours on an A100 to run a single chain. By comparison, you can train a VI model in about 40 minutes. So we need an approximation that gives us something that is reasonable compared to our HMC truth, if you like. So this is what we've been doing. Here's a comparison of some of the different approximations that are used in Bayesian deep learning. So at the top, we have our HMC, and I'm showing you the error, the performance. The error is a measure of performance here compared to variational inference, last layer Laplace approximation, MC dropout, ensembles, and then just the straightforward map value on the model. What I'm showing you next to it is something called the uncertainty calibration error. I don't know how, uncertainty calibration estimate, sorry. I don't know how many people are familiar with this, so I'll explain a little bit about what it is. But what you can see is that the HMC and the VI, they have similar performance. In fact, the VI gives us the best performance for this particular problem. They also have the best calibration in the sense that the smaller the UCE value is, the better calibrated your model is. And that's because the UCE is a very simple measure. It's just showing you the deviation from a linear relationship between that variance in the output compared to your error rate. So for example, the higher your variance is, the more often you would expect something to be misclassified. I've illustrated it with a toy diagram here where it looks quite random. In practice, what you can see is that certain models will systematically under or overestimate their degree of confidence when it comes to calibrating their errors. For those who are more familiar with this field, we've also looked at whether the data augmentation plays a role here, and we can see that it does play a slight role, especially with the HMC. This is important for a number of reasons, one of which is that Bayesian deep learning methods have been held up as a form of deep learning that can provide good performance with fewer data samples. That's obviously important when you don't have billions of data samples. The other reason why it's important is because data augmentation has also been held up as a problem for Bayesian deep learning models in terms of likelihood misspecification. And that is something that I'll come back to in a minute. So from these results, what they suggest is that VI is a reasonable way to go. It looks very similar to the HMC. It's much cheaper. However, there's always a catch. And the catch is that for our particular problem, we see what's referred to in the literature, or the computer science literature, as a cold posterior effect. And a cold posterior effect is a way of describing what is probably more widely a form of model misspecification, which means that you don't get optimal performance by implementing your posterior fully. You have to downweight your posterior when it comes to your optimization. So I'll explain this cold posterior plot in a bit more detail, but just to clarify the axes, what I'm talking about when I talk about tempering the posterior is that we introduce this temperature term T, which is just simply a power on the posterior, so it downweights the posterior term in your evidence lower bound objective function. So to view a bigger image of this, so all of the colored lines you can see there are for the variational inference models, and we've done this over a variety of different priors, with and without data augmentation. And what you can see is that we have to lower that temperature term quite significantly to get optimal performance out of our VI model. Now, we do not see this effect with the Hamiltonian Monte Carlo. So this suggests not as one paper we saw in the literature suggested, that Bayes' formula is wrong, but more likely that something is misspecified in our VI model. So as I said, there has been a number of papers in the literature that have looked at data augmentation as having an effect on your likelihood function. We don't see this effect, so we looked at augmentation, no augmentation, principal data augmentation has very minimal effects. We changed our prior choices. We looked at our posterior, so we assumed that maybe our posterior, our variational approximation was misspecified, which is, always possible. We chose a Gaussian. Everyone chooses a Gaussian. But in fact, our HMC posteriors for our parameters are very Gaussian. So we don't think that's our problem. It could be a mix of things, but what we're most worried about at the moment is stochastic gradient descent as our optimization choice. So our next approach here is to look at other forms of optimization for our VI. I should say that our cold posterior effects in other problems have been solved through changing the data augmentation or changing the prior. This is a problem-specific issue. And until it's solved, I don't think we can say that VI is the perfect solution to our uncertainty estimation. However, if we can solve this, then VI does look pretty good, although I suspect we may be trying parallel tempering quite soon. Aside from understanding the importance or the confidence with which different samples are actually predicted by our models, uncertainty is also important for a number of different other areas in astrophysics. So one of these is how we identify biases in our model predictions. So I'll give you what might seem like a very trivial thing in terms of biases. But if I have a radio galaxy, like one of these images on the right, so this is all the same galaxy, just, with the orientation changed. The orientation of the galaxy doesn't change the class of the galaxy. It's a Fanroff-Riley class 1 galaxy, regardless of whether it's upside down or on its side. And our model predictions should reflect that. However, if you take the same galaxy, which are these little images along the bottom, and you change the orientation at test time, you pass it through 200 times, then your softmax distributions for class 1 and class 2 in blue and red change as a function of orientation. And the reason for this is quite obvious if you are familiar with convolutional neural networks. One of the major reasons for using convolutions for sharing the weights is that they are translation invariant, but they are not invariant or equivariant to rotations and reflections. So what we're seeing here is a function of the convolution actually producing different features depending on the orientation of the galaxy. And this is true even if you use rotational augmentation in your training process. Just want to make that perfectly clear. This effect happens whether or not you use rotational augmentation. But once you know it's there, you can correct for it. And we did this using group equivariant convolutions, where we were equivariant to the isometries of the Euclidean group, which is rotations and reflections. And that means that you can go from this change in distribution as a function of orientation to a consistent classification as a function of orientation. Now, the reason why having that distribution of outputs is important here is because if you just have a single output from your model will give you a result for every orientation, but you won't see the pattern. And it can very, very confidently give you the wrong result. Just as a little extra bit about why this is important is that it also reflects back on the scientific problem that we're looking at. So we found that, in fact, just using rotational equivariance on our model corrected this effect for one type of galaxy, but didn't correct it as much for the other type of galaxy. So actually having the reflectional equivariance was very important here, and that is telling us something about our training sample, because astrophysically there's no reason why those two galaxy types should exhibit different behavior with respect to these different isometries. Then the other thing I wanted to highlight is how we can use uncertainty to preserve discovery, and I think this is incredibly important for astrophysics. And this comes back to those different Bayesian approximations. So when we talk about discovery, what we're really talking about is deciding whether something is in distribution. So our training data is our in-distribution data. It's our archival data. We know what's there. Astrophysically, when we build a new experiment, when we take a new observation, we are by definition looking at shifted data, because if it was exactly the same as what we already have, then we wouldn't bother. So we examined how sensitive these different Bayesian approximations were to different types of distributional shift in our data. Now, there are different levels of distributional shift and, of course, different types of distributional shift. So here what we're showing you on the right-hand side, the first two columns there, this is our training data. So where it says mirror best, where it's blue, that's our training data, that's in distribution. Now, if we take the same type of object, so a radio galaxy, but observe it with a different telescope, that's one type of distributional shift. So that's the green column where it says MIGHTY. This is the MIGHTY survey, is observations done with the Meerkat telescope in South Africa. The final column there, which we're calling Galaxy MNIST, these are not radio galaxies, these are optical galaxies. So these are star-forming galaxies that we could see with the naked eye if our eyes were as strong as our telescopes. So these are not only observed with a different instrument, but they are a fundamentally different type of galaxy. So this is a different type of distributional shift. But in practice, both of the two right-hand columns are out of distribution, if you like. So if we use models trained using different Bayesian approximations, at test time using a different Bayesian approximation, we can see how well those models are able to separate out these different types of distributional shift. Now, as you might expect, HMC is in fact the only method that we looked at that was able to completely separate out these distributions. So the green, blue, and yellow correspond to the green, blue, and yellow on the right-hand side. These are the energy scores for the different test samples. You can see that even VI has overlap between the different types of distribution, although it's better than the two approximations at the bottom. In particular, we found that Laplace confused the two types of radio data significantly. They overlap completely, which was very interesting for us. So this means that not only does the calibration of your uncertainty change depending on the approximation that you use, but also the degree to which you're able to distinguish different distributions will also change. Now, this is not necessarily a problem. As long as you understand how that works for your particular model, then you can use that in your analysis. However, it does become problematic when either people don't understand it or they are combining data that were produced by different models, in which case you are combining different biases and different calibrations on your uncertainty. So this is what we're working on at the moment. I just wanted to end by talking about where we're going with this work. So I think many people will be familiar with the scaling laws in deep learning that have led to this explosion of giant models that we're seeing at the moment. The same scaling laws that you see for language data and for vision data, we also see for astrophysical images. It's important for us to test this scientifically because computer vision scaling laws are all based on ImageNet data. And ImageNet data is qualitatively different from our astrophysical data as it is from domain-specific data in other fields like medicine. So it's not necessarily true that the same scaling laws will apply. However, we do find that we get these power law scaling laws as a function of data. However, when it comes to scaling as a function of model size, i.e. the number of parameters in your models, what we find is that in fact we saturate very quickly. And the reason for this is that we simply don't have the same volume of data, of labeled data, as you get in the highly curated CS datasets like ImageNet. And so in fact our work is the single largest astrophysical data set. It's the only scaling analysis on vision data that's been done outside an ImageNet context. And our data sets are an order of magnitude to 2 orders of magnitude smaller than those kinds of data sets. And that's never going to change, right, because of the cost of labeling our data sets. So for us, simply scaling up supervised models is not going to be the way forward. So what we've been doing more recently is using these foundational representations. And we use foundational representations built on self-supervised models, and we've been doing this for optical and radio astronomy, where we can then use the latent representation for multiple downstream tasks, or more importantly, we can fine-tune it on small volumes of labeled data, which we do have available for highly specific astrophysical questions. So the question we're now asking ourselves is, how do we propagate our uncertainties through these models, and what does the latent representation actually represent in terms of a predictive prior on those fine-tuned tasks? And so that is where we are going with this, because from our perspective, this is going to be the most important thing. And I'm going to finish on that note. I just want to thank the members of my research group, whose work I've been showing you throughout these slides. And in particular, I wanted to highlight Devona, who's in the middle there, who has done most of the work on the Bayesian models that I've presented here, and is in the audience. So please do chat to her if you're doing similar things. And I'll finish there. Thank you.
Thank you very much. I think we've got time for 2 questions.
Thank you. I actually want to ask about the first challenge on the list, which is label data. Is there any way, I mean, naively what you do, you'll get a stack of all the images and you'll just go through them one by one. Is there any way of figuring out which ones are most informative for your particular model? And I guess this applies across lots of things. I'm thinking of MRI data or whatever else. Are there standard methods in astrophysics?
So standard is a subject. There's no standard method. So for the scaling models that we did, where we're using a large volume of labeled data. So this data comes from the Galaxy Zoo project, which is actually a citizen science project. So there we can use the degree of consensus in the labels in order to determine which ones are, informative is the wrong word, but which ones we're most confident in our training. But then that brings you back to questions of how overly curated is your training data, or should you actually be including the low consensus labels in order to do some domain randomizations? That I'm not sure if that's the question that you're asking, but yeah, that's about it for this kind of analysis. Yeah.
We've got a quick second question at the back.
I don't know if you have faced this problem, but you have talked about like 50 years of data gathering, which could be possible. How do you deal with the technological changes, which changes the structure or the fidelity of data? Because like 1970s data could have lower resolution. Newer data could have higher resolution.
Yeah, so this is a good question. I mean, so the question is how do you deal with changes in the data that relate to the evolution of the instrument, I guess. And this is something that we already see in our training data. So the archival data that we work with comes from multiple different instruments that have different resolutions, different sensitivities. In radio astronomy, we're not just taking a direct image. In fact, what we do is we measure the Fourier components and then we reconstruct. So it's not just resolution, it's also what's the largest scale in the data and what's the sampling in Fourier space. So that will vary instrument to instrument. And it has some very interesting effects on transfer learning, for example. And the answer is that there is no good answer yet. We're still working out how these things bias the next question we ask. And I think that we will evolve as the data evolves, is the answer. Yeah.
Okay, I'm sorry, I can see there are more questions, but we're going to have to cut you off. Let's thank Anna again.